In this first video of today, we are going to go over how to draw Lewis structures. So I would highly recommend a periodic table if you don't have one right now. You're going to need it to figure out how many valence electrons different elements have. And so if you don't have a periodic table, make sure you grab one. Okay, so let's hop on in. So in bonding, obviously what happens is either electrons are shared or electrons are transferred from one element to another. And so there's kind of two models that we have that basically explain what's happening in bonding, or two accepted models. So the first one is the molecular orbital model. And basically, this is saying that our electrons are in orbitals in a molecule, much in the same way that they occupy orbitals in atoms. So kind of in these different orbitals in that bonding. And basically, electrons do not belong to any one atom. So once they're in that bond, it's no longer like, well, that was carbon's electron, that was oxygen's electrons, but instead they just kind of go where they please between the two elements. This is a very complex model, saying that they're in orbitals. Now then the other one that we see is the localized electron model. That's probably the one that you're a little more familiar with, and really kind of the one we base our Lewis structures off of. And so we say that molecules are composed of atoms that are bound together by sharing pairs of electrons using the molecular orbits of those bound atoms. This is the more traditional model of showing, like, drawing the bonds and all of that stuff. It's a little simpler. Okay, those are just kind of interesting to know, not like need to know. Okay, now when we are drawing these structures, there's things you need to know. So you definitely need to know what a lone pair is. And a lone pair of electrons is a non-bonded pair of electrons, and it's localized to one atom. So we draw them in the Lewis structures as just little dots. That would be a lone pair. And then a shared pair or bonding pair are electrons that are found in the space between atoms, and we draw those as a line in our Lewis structures. And Lewis structures, their point is that they show how the valence electrons are arranged, so that we're able to basically, well, I don't even know what I'm saying. Let me try that again. Lewis structures show us how the valence electrons are arranged. And basically, the point of Lewis structures is that what we're trying to show is the formation of that stable compound, so that they achieve those noble gas configurations. Only valence electrons are included in Lewis structures. We don't draw all the electrons. We only draw the valence electrons. So we're going to start by just doing these electron dot notations. So we're going to start by doing these electron dot formations or dot notations. These only show the valence electrons of a single atom or element. So we're going to start with looking at the electron dot notation of an atom, and it only shows the valence electrons. So let's start here with sodium. So sodium is in group 1 on our periodic table over here in the alkali metals. So that means sodium has one valence electron. So sodium would be drawn with just one dot around its side. Magnesium is in group 2. So magnesium has two valence electrons, so it would have two dots. And you do have to put a dot on each side before you pair up. Boron is in group 3A or 13, so it has three valence electrons. All right, carbon, group 14, has four valence electrons. Nitrogen has five valence electrons. So now we have that pair. Since we had one on every side, we then could pair up on the top. Oxygen has 6. And fluorine has 7. And neon has 8. Okay, that's how we draw Lewis structure, or basically kind of Lewis electron dot notation of individual elements. So now we're going to start by doing ionic compounds. I think ionic compounds are really, really pretty simple. So first up, we're going to draw the Lewis dot structure for the positive ion with charge outside of the brackets. If there's more than one positive ion, draw them all. and then draw the Lewis dot structure for the negative ion, again with charge outside the brackets. If there's more than one, draw them all. So this is kind of an example of what it looks like. You guys can see we have our potassium and we have our chlorine. When they react together, they form that positive potassium with that negative chlorine. And potassium donates its electron to the chlorine, causing it to have a full shell. And then potassium has lost its valence electrons, but it's still, because it's lost that valence electron, it's then down one energy level, which should be full. So let's start with this first one. All right, it says draw the Lewis dot diagram for a compound between a calcium ion and a sulfide ion. So calcium is Ca with a positive 2 charge. Sulfur is S with a negative 2 charge. If I was writing their formula, I would need to swap, drop, reduce, and so that gives me CaS as my formula. Okay, I'm going to show you guys what actually is going on in the Lewis structure before we draw it, like why this is our final Lewis structure. And then for the next ones, we're just going to draw them normally. So we're going to start with calcium, and calcium is Ca, and normally calcium has 2 valence electrons because it's in group 2. And then we also have sulfur. Sulfur is S. I'm going to draw it a little further away. S, and sulfur has 6 valence electrons because it's in group 16. All right, so what happens is when they form those bonds, all right, calcium is going to donate its 2 electrons to sulfur. And so then calcium, because it's donated those 2 electrons, sorry, having some technical difficulties, it now has lost its valence shell. But since it's lost those 2 electrons, it leaves calcium with that positive 2 charge. And then sulfur had 6 valence electrons, but it gained 2 of calcium's electrons, which then, leaves sulfur with that negative 2 charge. Not so bad, right? Okay, let's do our next one. So this next one is between potassium ion and an oxygen ion, or oxide ion. So potassium is K, and it has a +1 charge. Oxygen is O, and it has a negative 2 charge. Swap, drop, reduce to get our formula, and we get K2O. Okay, so now let's draw our Lewis structure. So we should have 2 potassiums and 1 oxygen from our formula. So let's draw our Lewis structure. So first off, we have potassium. It's got a positive charge. So that means it's lost its valence electron. It's going to be K with a +1. There are 2 potassiums, so we need to draw both of them. And then we have oxygen, and oxygen has a negative 2 charge. So it's going to be like this. That negative 2 charge means it's gained 2 electrons. So where oxygen normally has 6 valence electrons, it's got a negative 2 charge. So that means it's gained 2 more. So that means it has 8 valence electrons now. And that would be our Lewis structure. And sometimes you'll also see it just written as like 2K and then the O, and that's fine too. Okay? So I want you guys to pause the video and try to draw magnesium fluoride on your own. All right? Okay, guys, so hopefully you swap, dropped, reduced, and we got our formula is MgF2. Since magnesium has that positive charge, it should have no valence electrons. Fluorine has that negative charge because it's gained 1, so each fluorine should have 8 valence electrons drawn around it, bracketed with the -1 charge outside. And that's how you draw ionic Lewis structures. I think they're pretty easy. And I sometimes like to write them like I did the magnesium fluoride with like the 2 fluorines stacked, just because I personally feel like it looks a little less awkward, but it's fine either way. So that's ionic compound Lewis structures. All right, so now we're going to jump into covalent. And we're just going to start with the basics in this video, and we'll jump into the harder problems in our next few videos. Okay, so Lewis dot structures of a covalent molecule. Basically, a couple things you need to know is the duet rule. So hydrogen only basically wants 2 valence electrons. And then He doesn't form bonds because it's already got a full sublevel, so we don't worry about helium. So hydrogen's the only one that has the duet rule. And then pretty much everything else follows the octet rule, which says they need 8 electrons to complete their valence shells. Okay, so let's go through the rules. So step 1, you need to add up your total number of valence electrons for all atoms. Step 2, decide who is the central atom. It's going to be the one with the lowest electronegativity, but typically also in our Lewis structure, it's going to be, struggling with words. It's going to be the one that only has 1 in the Lewis structure in the compound formula. So it'll typically be the only one that only has 1. Hydrogen is never, ever, ever the central atom. And then if you have carbon, carbon is always your central atom. So then we're going to draw bonds between the atoms after we figured out our central atom. Fill all your octets, except for hydrogen, who only wants 2, and boron, who only wants 6. Place electrons that are left over on the central atom in pairs. Make sure all the electrons has at least an octet. It could have up to 12 pairs of electrons in some cases. It's pretty rare, and we'll talk about those strange cases in a minute, in our next video, actually. But yeah, if you don't have at least an octet and the central atom is not boron, it will resonate to satisfy the central atom, which again, we'll talk about in our next video. If the particle is an ion, be sure to place it in square brackets and put the charge outside the brackets. And then sometimes we have to make double bonds if we don't have enough electrons. Okay, so let's start with our first example here. So in our first example, we have H2S, and it's already calculated all the valence electrons for us. So hydrogen has 1 valence electron, and we have 2 hydrogens, and sulfur has 6 valence electrons, and we have 1 sulfur, so that gives us a total of 8 valence electrons. Since hydrogen is never the central atom, we automatically know that sulfur is going to go in the center for us. Then what we're going to do is we're going to go ahead and bond our hydrogen on either side of our sulfur. All right, so at this point I need to count how many electrons I've used. I have 2, 4, so I've used 4. I still have 4 more to go. So once I've used them and I've put them in bonds, I'm just going to fill up, use the rest of them on my center atom. So 1, 2, 3, 4. So I've used all 8 electrons, and now what I need to check is, does everybody have an octet or a full valence shell? So right here, this line counts as 2 electrons, and it's going with my hydrogen. So yes, that hydrogen has 2 valence electrons. That hydrogen is stable. All right. Then we check the same thing over here. That hydrogen has 2 electrons. So that hydrogen is stable. And now we'll check our sulfur. Our sulfur has 2, 4, 6, 8. Sulfur is satisfying the octet rule. So sulfur is full. So that sulfur is good to go. All right, now we'll talk about VSEPR shapes, but you guys may remember from last year a little bit that really how we would draw this is actually with the sulfur with 2 up top and then the H at the bottom. So if you think about your VSEPR shapes, if you remember those, but we'll also talk about those next class as well. Okay, so then we have CO2. All right, in CO2, we have carbon has 4 valence electrons, and we have 1 carbon. Then we have 2 oxygens, each with 6 valence electrons, giving us a total of 16 valence electrons. All right, so our carbon is going to go in the center, and we are going to bond our oxygens to our carbon. So far, I've used 4 electrons, and I have 12 more to go. So I'm going to fill my outer atom's valence electrons, and then any of the remaining ones we'll put on the center atom. So I'm going to go 2, 4, 6, 8, and that will fill up the oxygen. Oxygen, 2, 4, 6. This oxygen's full. So now we're going to check for octets. So for my first oxygen, I have 2, 4, 6, 8. First oxygen's good. Second oxygen, 2, 4, 6, 8. Second oxygen is good. Check carbon, 2, 4. Well, Carbon still needs a full valence shell as well. And so what we do in a case like this, whenever we've used all of our electrons, we can't just add more electrons randomly. What we're going to do is we are going to steal a lone pair and put it in between and create a double bond. So now carbon has 2, 4, 6, and this oxygen still has 2, 4, 6, 8. So we're going to do it on the other side as well. Oops, erased my oxygen. Do it on the other side as well, still that lone pair, and create a double bond. And now everybody has 8 valence electrons, and everybody is stable and is following the octet rule. So we're good. All right, let's do a few more examples. Okay, guys, let's do NH3. So far they've always had our valence electrons calculated for us. This time we have to calculate them on our own. So let's start with nitrogen. Nitrogen has 5 valence electrons. We have 1 nitrogen, plus hydrogen has 1 valence electron. We have 3 hydrogens. So this gives us a total of 8 valence electrons. All right, nitrogen is going to be our central atom because hydrogen can never be our central atom. So I'm going to put nitrogen in the center. Then I'm going to go ahead and bond 3 hydrogens to it. Now, I've used 6 electrons at this point, and I have 2 more that I can place. Each hydrogen is already full because each hydrogen has those 2 valence electrons around it. So I'm going to put those 2 electrons, the 2 extra electrons that I have, on my nitrogen. So each hydrogen then has the duet rule satisfied, or 2 valence electrons, and then my nitrogen has 8 valence electrons, and so this Lewis structure is good to go. Okay? Now then we're going to do HCN. This one's a little more difficult. So on this one we have hydrogen. Sorry, I don't know what I was doing. So we have hydrogen. We have 1 hydrogen, and it has 1 valence electron, plus carbon, and carbon has 4 valence electrons, and we have 1 carbon. And then finally nitrogen, and nitrogen has 5 valence electrons, and we have 1 nitrogen. So we have 1 plus 4 plus 5 gives us a total of 10 valence electrons to work with. Carbon is going to be our central atom, so we're going to bind nitrogen on one side, hydrogen on the other. At this point, we have used 4 of our valence electrons. We still have 10 more to use, so we're always going to fill our outer elements first before going back to fill in the center. So I'm going to fill up my nitrogen. Okay, so my nitrogen is currently full. All right, but my carbon isn't. So once again, I don't have any more electrons to add, so I'm going to steal a pair from the nitrogen and create a double bond. So now nitrogen still has 8, carbon has 6. So we're almost there, but we have to do it one more time. We're going to steal a pair from nitrogen and bond it to that carbon. And so now our nitrogen still has 8, carbon now has 8, and hydrogen has 2. So everybody is satisfied and stable with their correct number of valence electrons. Okay, we're going to do 2 more in this video. I'm going to do 1 more with you guys and then leave 1 for you guys to do as practice. And then after that, I'm going to end this video. There'll be another video about exceptions and formal charge. Okay? So we're going to do NO. All right, so we know nitrogen has 5 valence electrons, and we have 1 nitrogen plus oxygen that has 6 valence electrons, and we have 1 oxygen. Now, that positive sign tells me that I have lost 1 electron. So I have 5 plus 6 minus the 1 electron we've lost gives me a total of 10 valence electrons here. Now, I just have nitrogen and oxygen, so they are both, there's no central atom there, so I'm just going to bond them together. These 2 valence electrons, let's try to start filling up our octets. So there's 4, 6, 8, 10. All right, so this leaves nitrogen with a full shell, but oxygen only has 4. So once again, we're going to steal a pair, create a double bond. Now oxygen has 6, while nitrogen still has 8. So once again, steal a pair, create a triple bond now. Now both of them have those full valence shells satisfied. But because this one is an ion, we need to put it in square brackets and include the charge. So it's going to have a positive charge. All right. So I want you guys to pause the video now and try to complete carbonate on your own. Okay, guys, hopefully you got to this point at least and you realize, so I've used all of my electrons, but I don't have enough on my carbon atom. So once again, we can steal a pair from one oxygen, and it doesn't matter which one, and then create that double bond. So then everybody has that full valence energy shells and they're stable. Don't forget to draw brackets. Okay? All right, guys, hopefully this was a good review for you guys and you kind of remember now a little bit more about Lewis structures. In the next video, we're going to go more into exceptions as well as resonance. So definitely check that video out. Okay, bye, guys.